Hello, everyone. My name is Kathleen from the Gurobi marketing team. Thank you for joining us for this special hour launch event on our latest release, Gurobi 10.0. There will be time reserved at the end to answer questions. Please feel free to submit your questions using the Q&A feature. If we cannot respond to your questions directly, we'll make sure to respond to you individually shortly after. Today, you will be hearing from Tobias Achterberg, VP of Research and Development, and Michelle Jasinski, Director of Cloud and Platform Research and Development from Gurobi Optimization. Without further ado, I pass it over to you, Toby.
Thanks, Kathleen, for the introduction. And hello, everyone, to the webinar on the new version of Gurobi, Gurobi 10.0. So I have Michelle Jasinski here with me, the head of our so-called platform team. And we have also David Torres-Sanchez and Robert Lutze to help you and answer questions that come online. So please feel free to post your questions in the Q&A panel, as Kathleen said. And then some of them Robert and David will already answer online, while others will be held back for the Q&A session at the very end. Okay, let's get started. Here's the agenda for today. So Gurobi 10, as always, includes a number of new performance techniques that I will explain a little bit, partly some of them. Then we have exciting new platform features for the cluster manager and for our web license service, WLS. We have added in new API and engine features on top of the performance, and pretty cool stuff. We have open source GitHub repositories now online that you can use together with the Gurobi releases. So let's dive into the new performance techniques. So here's the overview of the performance improvements that you will see after installing Gurobi 10.0, comparing it to the previous version, Gurobi 9.5. So you see here on the linear programming test sets, we have achieved some nice speedups. In particular, for the default settings, which is the concurrent LP solver, we have a 10% speedup overall, and on the harder models, so those that take at least 100 seconds to solve for one of the two solvers, so 9.5 and 10.0, we have achieved a 25% performance improvement. And then the probably most important aspect always is mixed interlinear programming. Here we also have a nice 13% improvement, 24 on the harder models. And then for the quadratic problems, the improvements are even larger, in particular also for the non-convex MIQCP problems, where we have added support in Gurobi 9.0, and now with 10.0, it's even faster than back then. Okay, let's start to look at some of the performance improvement features that we got for linear programming. So here is an overview of the ones. So, and I will only talk about the first two listed in red. So the new network simplex algorithm and the concurrent LP improvements. But we have also some improvements in crossover, in particular that the primal pushes are now parallelized, and the barrier solution is slightly adjusted before the pushes so that the crossover becomes faster. And we have new and improved pre-solve reductions. In particular, we have extended some of the reductions that previously only existed for mixed integer programs to linear programs, in particular the pre-sparsify reductions. This LP pre-solve is a little bit more complicated because there you also have to deal with the dual solution and the basis, and you need to be able to uncrush such that you get a dual solution and also a basis for the original problem. For that reason, it's more difficult, and this is something that we have extended. And the aggregate parameter now has a new value too, which makes it more aggressive also for linear programs. But let's look at the new network simplex algorithm. So here, a network problem, that is a very special type of an LP. So for you as a user, there is no change at all. You just specify your problem as always as a regular LP. But Gurobi will then identify that this is actually a network flow problem, a minimum cost flow problem. And then we just launch the network simplex algorithm automatically if you set the corresponding parameter. So, and the motivation is that this is a very well-known problem, min cost flow. There are very many different algorithms to solve it. And in particular, one of those algorithms is the network simplex algorithm. And this comes in a primal and a dual form. And we have in Gurobi 10 implemented the primal network simplex. Okay, so how does it work? Just very roughly. So given is this network problem, so that has nodes and edges, of course, and flows. You should set flow through the network. And how is it working? So the most challenging part of the implementation is to deal correctly and efficiently with this data structure for spanning trees, because the spanning tree in such a network, that is the counterpart of an LP basis. And then you need to do all the basis updates as corresponding switches in the spanning tree. So going from one basis to the other means remove an edge from the spanning tree and add some other edge so that it is again a spanning tree. So these are the steps. So this is pivoting in the network algorithm. And the advantages of the primal network simplex over the general LP primal simplex is that with this special data structure, the computation is much faster, because this is really a completely combinatorial algorithm then, so no LU factorization, no linear system solve, and so forth. And so that means one pivot is about 5 times faster than in the general LP primal simplex. There's a guarantee that you get no cycling here, and it's easier to construct special algorithms to design a good initial spanning tree, which is in the LP simplex would be the basis crash procedure. And if you look at the performance on our network test set, then compared to the general simplex, primal simplex algorithm, it's 36 times faster, this network algorithm. And dual, of course, is the better simplex algorithm, but even regarding to dual, it's almost 4 times faster. There is also the dual network simplex algorithm, but this is we did not yet implement. So there would be similar difficulties to implement it, but even a little bit harder. So we currently don't know any simple and nice way to guarantee that there is no cycling. If we were to implement it, we would expect it to be faster than the primal network simplex algorithm, but as I said, we did not yet do that. Okay, concurrent LP algorithms in Gurobi 9.5. First, let me explain that so that I can then tell you what the difference to 10 is. So here's just a regular dual simplex solver, right? The steps that you have. You start with the original problem. Then usually you would apply pre-solve. Of course, you can turn that off as well, but this is usually you would do that. Then you get the pre-solved model, and then on the pre-solved model, you apply the dual simplex procedure, which produces a solution for that pre-solved problem. And then you need to uncrush that solution and the basis, and this gives you an original solution with an original optimal basis. This is what you want. And of course, there are now many steps in between that you can add to improve performance. So on the one hand side, you can, instead of working on the primal problem, you can form the explicit dual. If you want to do that, then you have to build this dual model. And then the next step after pre-solve could be that you exploit symmetry to perform a step that is called symmetry folding. That gives you another model, smaller model, that is kind of equivalent to the original pre-solved model. Then on that model, you perform another pre-solve operation that gives you the pre-solved folded model. And then you apply the dual simplex, and then you need to uncrush everything through this whole chain of reductions, and in particular in between, after you have found uncrush the final pre-solve, then you have to perform a crossover step to get from the symmetric folded problem to the regular pre-solved problem, and then another uncrush to the dual solution, and then you need to dualize in order, if you had dualized the problem, to get to the original problem. Okay, that's a long chain of stuff. And now you want to use concurrent, so you add primal simplex to the mix, which is doing exactly the same stuff. Just in the end, it would apply primal simplex instead of dual. And then barrier, which is also doing almost exactly the same stuff. The difference in barrier is that the decision whether to dualize or not is slightly different, because barrier behaves a little bit different. So the tuning is different in that decision. And also the pre-solve steps in barrier are slightly different to what the pre-solve for simplex is doing, because barrier likes certain things that simplex does not like, and vice versa. Okay, but other than that, it's really the same running in parallel in the threads. And so we thought, well, why do we do this? Almost the same 3 times here in parallel. We should just do it only once. And this is what we have done in Gurobi 10, right? So the issues here is you make a copy for each of the concurrent jobs, and that already takes a lot of memory. And then each of these jobs are applying all these steps independently. And that can actually slow down the whole process quite significantly if you have just a single CPU with multiple cores. Depending on the machines and the CPUs and the size of the model, just running other stuff in parallel that is useless work can slow down the main solver by 30 to 60%. So now we decided to change that completely in Gurobi 10. So we would only apply the concurrent solves at the very end in parallel. All other steps are executed sequentially. So that means you have only the model once in memory here, all these intermediate models. So that saves you a lot of memory. But there are a few challenges, namely, as I have said, there are different decisions depending on barrier or simplex, whether you dualize, and also slight changes in pre-solve. So this has then to be tuned a little bit to get it right for both, somewhat right for both. And the speed up by having that for larger models is often much more than 10%. So the 10% was the speed up that we got overall, but for large models it can be much more, and in particular because it uses now much less memory, right? Because the big parts are here these initial models that have to be copied for a 9.5. Okay, now the MILP performance improvements. This is typically, as usual, a very long list, so we only list here the main ones, and there are a number of tiny changes, small changes that improve performance only a little bit, but still they sum up. And from this list of things, I will only talk about the first one, the strong branching improvements. We have also added various symmetry improvements. Then an interesting one is to disable inactive cuts for the relaxations solved at the nodes while diving, and then dynamically enabling them again when they are useful and so forth. So that was a nice exercise in data structures and implementation, and it also gave a nice performance boost. Solving submaps is now done more aggressively. As always, pre-solve is a way to improve performance, and adding new reductions almost always helps. The concurrent LP improvements also gives us a little bit for MIP. And there is using emerging cliques by aggressive variable upper bound usage is a new technique. And OBBT, optimization-based bound tightening, that is one that also helps for MIP, but this was mostly implemented for MIQCP, and in particular non-convex MIQCPs, because there it really helps. But for MIP it also helps a little bit. But we will discuss that later when we talk about the non-convex MIQCP performance improvements. Good, but let's talk about strong branching. So strong branching is a branching rule, or is used as part of the branching rule, where you need to decide which of the fractional variables you want to select as the branching variable. And what you do with strong branching is you just apply on each of these candidates a few dual simplex pivots in order to see how the objective function is behaving. And then you would select the variable that is kind of improving the objective function the most in both directions. So for each of the variables, you perform a certain number of dual iterations in the down branch and the up branch, and then the objective changes tell you which is the variable that is the best. And now for Gurobi 10, what we have improved is we try to make that a little bit less expensive, so that we, in the end, can apply more strong branching because it's less expensive, each individual one. So how do we do that? So one thing is the look-ahead strategy. We have now also implemented that is in other solvers as well. So what you do is you just, when you have a list of, let's say, 100 candidates, you would apply the strong branching one after the other. And if, for example, you found a new best candidate, and then the next 10 candidates are not as good as the one that you have found, and then you just stop. So after, let's say, 10 candidates that you have tried that did not improve the current best candidate, you just stop. So, and then this is a small performance improvement because you do less work. And then another thing is you can look at the symmetry groups. And of course, when you have already applied strong branching on one candidate, and then you would want to apply it on another candidate that is symmetric to this candidate that you have already tried, that is of course a waste of time, because if you were solving the LPs to completion, then it's clear that you are going to get the very same results, right? So we just skip the symmetric candidates now. Another trick is to combine the strong branching with implications from branching down or up. So we have implied bound tables, clique tables, and SOS constraints. So before actually then solving the LP, we would propagate these tables. Those are quick to propagate. And so it's a nice way to then get stronger bounds from strong branching, because you have some of the integer implications now included. And we have tuned the decision on how often to apply the strong branching, because now with the improvements that it's less work, we can apply it more often, and various other tweaks. So strong branching is now more efficient in Gurobi 10. Okay, this is what I wanted to say about the MILP performance improvements. Now let's come to the quadratic parts. So convex MIQP, so that these are the problems with a quadratic objective function, and convex MIQCP, those are the problems where we can also have quadratic constraints. And there we have a number of performance improvements as well. And here I only like to talk about the very first one, the new Cubo heuristic. But we have also improved the perspective strengthening that we do. Then another trick is to move the quadratic objective terms into constraints in certain situations, because then you can then you can add cuts and so forth, and sometimes it works better. There are some work limit adjustments for the heuristics, strengthening of coefficients for binary variables in quadratic constraints, right? So similar what you do to linear constraints, lifting in binary variables, you can also do for quadratic constraints, and this is what we have implemented. Then certain improvements in heuristics. Then for the linearization, so if the quadratic terms involve at least one binary variable, then you can linearize them. And if they are actually, if it's products of two binary variables, then you have a choice of how to linearize. And here you can solve a set covering problem to find kind of the best selection of binary variables to linearize. And this is what we do. This helps a little bit as well. Remove common variables from quadratic terms. That is one pre-solve reduction. And again, OBBT here comes into play a bit more than for MILP. Still, we are going to talk about that when we cover the non-convex MIQCP stuff. And the MIP improvements that we have also apply, of course, to MIQP and MIQCP. So let's talk about this Cubo heuristic. So Cubo, that means a quadratic unconstrained binary optimization. So this is a very special MIQP, namely one where all the variables are binary and there are no constraints. And when we talk about heuristics, you always have to understand that there are two types of heuristics, namely construction heuristics that just create a new solution out of nowhere, and then improvement heuristics that would allow you to take an existing solution and find a better one, usually in some neighborhood of the existing solution that has a better objective function value. And in Gurobi 9.5, we only had an improvement heuristic based on taboo search. So you start from some random starting point, so usually the current solution, and then you apply steps to find a better solution. So this is local improvement, and this is it for Cubo. It's very easy because there are no constraints, right? So every solution that you encounter is feasible. It could just be that it has an inferior objective value. In Gurobi 10, we have added a new Cubo heuristic. So this is the rank 2 relaxation heuristic, a construction heuristic that was published in that paper here mentioned by Bura, Montero, and Zhang. We just implemented that, and that works really very well. So, and one interesting aspect about Cubo is that this is the computational model of quantum computing, right? So if somebody tells you I have a problem, I solve it with quantum computers, then you can say, oh, just give it to me, I can solve it with Gurobi. And usually the Gurobi part will probably be faster. Okay, so why having two heuristics? Well, it's always good to have multiple things because sometimes the one works good, sometimes the other. So in particular, the neighborhood search of the taboo search can be defeated when the good solutions are very far apart. And this is particularly important when constraints are captured as penalties, right? So when you actually have a problem that has constraints and you would turn that into a Cubo, you have to put the constraints into the objective function by adding penalty variables, so in a Lagrangian relaxation fashion. And then it makes that the feasible solutions are far apart, and that means for the Cubo heuristic, the good solutions are very far apart, and then the neighborhood search often does not work so well. And our computational results on the Cubos that we have is that we are now able to find good solutions for Cubo problems very quickly, and it in that case, these heuristics also reduce the optimization time, so time to proven optimality significantly. And this is pretty surprising because that is for heuristics usually not the case. Often heuristics only help you to find good solutions quickly, but not to improve the dual part of the optimality proof. Okay, let's switch to the non-convex MIQCP. So now here, as promised before, we are talking about the optimization-based bound tightening procedure, but we have also other performance improvements here. So for example, when the product terms that appear in the quadratic constraints, when we want to linearize them, then in some cases, these product terms form bipartite graphs, and then we explicitly deal with those to find a better way of linearizing them or to turn them into bilinear constraints. So this is one step in the transformation from a general non-convex MIQCP into this bilinear form that we can then actually solve. And we have also improved our NLP interior point heuristic, in particular the determination criterion, so that it is now better able to find feasible solutions. And we have added a multi-start feature to this NLP interior point heuristic. And then, as before, many MILP and convex MIQCP improvements also apply to the non-convex case. But let's talk about the OBBT. So optimization-based bound tightening, that is a very common technique for MI-NLP solver. So you start with your LP relaxation of this non-convex MI-NLP. So if you look at the picture, so here that you have this non-convex function, and also the solution should be in that polytope here, so linear constraints are there as well. And then you have a variable x, let's say this is between L and U initially, and then the OBBT says I now solve the linear relaxation and maximize x and minimize x over that relaxation. And then when you do that, you find that that you get tighter lower and upper bounds. So this is of course nice, just tighter and lower upper bounds for variables often help, but in that non-convex case, you get an even better improvement from that, namely that the linear relaxation, so the outer approximation of the non-convex constraints heavily depend on the bounds, and this then also becomes tighter if the bounds become tighter. Because now when the bounds are shifted like that, then the linear relaxation, so the outer approximation, the McCormick relaxation of that linear constraint is now much tighter, as you can see here in that picture. Okay, and for non-convex MIQCP, this gives us a 14% overall improvement and a 33% improvement on the models that solve in more than 100 seconds. For MILP, we have added additional improvements to make good use of that. Namely, we detect variables that influence big M coefficients. So in particular, the variables that trigger variable upper bound constraints. And because these continuous variables that appear in these big M coefficients, those are the ones where you want to have tighter bounds, because then you can reduce the big M, right? And this is why you apply OBBT also to those. And this is in particular important when you look at neural networks that have a ReLU activation function, because there you always have these big M constraints triggered by these binary variables in each of the neurons in the neural network. And that technique just gives a modest over average improvement for MIP, but for these problems that come from neural networks, this is a big improvement. Okay, and when we talk about non-convex MIQCP, I always like to show this graph here. This is the overall performance improvement that we got since the initial version 9.0, where we started to support it, and now with version 10, it's I think, 75 times faster in that particular part 10 measure that we used, which we think is a reasonable measure for comparing historic performance numbers, 75 times faster than the initial version. And also, if you look at the number of models that can now be solved, it's many more models can be solved. So only 10 models in our test set that any of the versions can solve cannot be solved by 10. And with that, I give the floor to Michel, who is now explaining nice new features of our platform components and the web license service. So Michel, please.
Yes, thank you, Toby. So first, I would like to talk about the cluster manager and the compute server new features. So the Cluster Manager and the Compute Server provides a client server architecture where you can deploy your optimization applications. It provides a web user interface, it handles the security and manages a set of nodes in the backend where you run your optimization. So in that environment, we have added two new dashboards in the Cluster Manager, the job dashboard and the node dashboard. These dashboards are used to better understand your applications, how they run, and also how you use your cluster. So let's get started and look at the job dashboard. When you open the job dashboard in the Cluster Manager, you can filter the data that you are looking at. You can look at what happened in the past 24 hours or 7 days or 30 days. And then you have at the top some global metrics. You can know how many jobs were executed, what were the total execution time, the number of active applications, the number of users who connected and submitted these optimization jobs. And below that, you have a set of distributions. You can quickly understand what are the different job statuses that you got, the solve statuses, and the different applications that were executed. And you see a number of jobs that for each application, a number of users, and runtime. And when you click on one of those label, you can also get directly to the jobs that are in this distribution. You also have below the timeline where you can display what happened over time in your cluster. Here, I'm showing in this screenshot the different applications that were executed over time in the cluster, and so you can very quickly pinpoint, something that happened where you had a peak usage from a given application, and using the labels, you can again zoom and drill down and know exactly what's going on into your cluster. The second dashboard is a node dashboard. In this dashboard, we focus on the nodes and how they run. So you will get the same type of filters, but you will get some different metrics. You will get the CPU usage, the memory, and number of jobs, and number of jobs in queue. And then you have, as before, some timelines where you see the CPU usage over time in the cluster for each node, and you have also other timelines. Next slide, please. You have the memory usage timeline, the job in queue, and the running job. So with that, again, you can understand where you had a peak usage. You can pinpoint to something that happened there. What's very interesting, for example, is to know when you have jobs that are going into the queue, because maybe it means that you are sending too many jobs at that time, or you may have to increase the capacity of your cluster. Then second item I want to cover is the improvement that we made on our web license service. So the web license service has been introduced with the Gurobi 9.5. We have servers all over the world running, and when you want to use Gurobi software, it connects to the servers and activates automatically Gurobi depending on your license types and capability. So it's very easy to use because you have nothing to install, and it runs in different types of environment. So in Gurobi 10, we support different types of deployment. We support containers such as Docker and Kubernetes environment, as we did in 9.5. But we also have added the capability of running on machines. So we can use this license type on Linux, Windows, and Mac. And you can even have some types of licenses where you can use containers and machines at the same time. So in conclusion, this web license service can now be used in different deployment scenarios as long as you have connectivity over the internet. And we also have added new reports in the WLS manager. So you can now see your usage in terms of platforms, in terms of versions. And we have improved the display of the usage over time with this timeline where you can see the different sessions that you are running with Gurobi. we also added some parameters to better control how we refresh the tokens and how WS is working. And thank you, Toby, and back to you.
Okay, thanks, Michel, for that overview. So, and after having talked about the performance features and the WLS and platform components, I'd like to now cover a few of the new features that we have added to the engine part of Gurobi and to the API. And the two that I want to talk about is the new logistic general constraint and the greatly improved version of our matrix-friendly API of Gurobi Pi. Other things I'd just like to mention are that we now have a NuGet package for .NET, so similar to PyPI with .NET, you can now also use that package system NuGet to grab and install Gurobi. And we have added a new version of the memory limit parameter that allows you to set a memory limit and then still get a graceful exit so that afterwards you can access the best solution, change the memory limit, resume optimization, and so forth. Okay, but now let's look at the new logistic general constraints. So our general constraints have been introduced in previous versions of Gurobi. So, and you can consider that these are two different types. So one is where the general constraint is basically just a helper to allow you to express certain functions as a general constraint, and Gurobi will automatically turn that into the equivalent mixed integer linear programming formulation. So, for example, the max constraint or the absolute constraint, these are two of such constraints. But then there's also another class of constraints which are more highly nonlinear, like exponential, sine, cosine, and so forth. And for those, we have also in previous versions added the support that you can specify that function, and then Gurobi will automatically perform a piecewise linear approximation of that. So that means this problem that Gurobi will solve will no longer be the exact problem with these nonlinear functions, but just a piecewise linear approximation of that. But this is then done automatically. And one additional function that we have added to the mix is the logistic function. And this is the one that you see here. So now you can state that as well as a general constraint. Okay, coming to Gurobi Pi. So there are a number of really nice enhancements that we did in Gurobi 10. So up to version 9.5, the support for multidimensional modeling was relatively limited, and some things just did not work. It gave you strange error messages and so forth. And if you are really a NumPy, SciPy expert user, then maybe some of this was annoying to you. And I guess now with Gurobi 10, almost all of these issues now are resolved. So we have greatly improved this interface so that many of these operations that you are used in NumPy will just work out of the box also with the Gurobi Pi modeling objects. So all of the mvar, mlinexpr, and mquadexpr objects support arbitrary dimensions, and adding constraints from such expressions yield multidimensional constraints or quadratic constraints. So here's an example, right? So you just with NumPy NP you build now some matrices with dimensions 4 and 3 and 4 and 6 in that example, and then you add an mvar, which is a matrix variable, right? So a matrix consisting of Gurobi variables with dimensions 3 and 6. And then you would set an objective function, but then the main part here is the add constraint function. You do this a multiplied by x larger equal to b, and you see here in the picture how that works, right? So the a and x matrices, they need to fit in dimensionality. So the 3 and the 3 here should be identical, and then what you get, of course, is a 4 by 6 matrix, and the right-hand side for that reason needs to be 4 by 6. And what does it mean? Well, this will automatically generate you 24 linear constraints in matrix notation. Then also for one-dimensional vectors, you can also do here some more stuff. So here's a quadratic constraint. So again, you have a matrix variable, dimension 8 by 3 in that case. And you have another matrix variable that is just one dimensional. So this is just is a vector of 8 entries, right? And then with that one single function call here, you can add 8 standard codes, right? So the sum of over the first axis, that will sum up the values in along the first axis. So this gives you an 8x1 vector, and then you take the square, so you sum up the squares here, right? And then you say this is smaller or equal to the right-hand side vector, each individual component square. So this gives 8 standard cones, each with sum, so x1 plus x1 square plus x2 square plus x3 square, smaller or equal to z square, right? So that is what is written there. And then broadcasting, that is something that NumPy users are very used to, and now this also works with Gurobi objects. All of these modeling objects can be broadcasted, and what does it mean? So operations with scalars and ND arrays and sci-fi sparse matrices support already, of course, support broadcasting, and now the Gurobi objects as well. So here's an example. So if you have a matrix variable, so 3 variables, right, a vector of 3 variables, each with an upper bound of 1 here in that example, and then you have a single variable. So this is a matrix 1x1, so to say, right? And then when you add, you can now take the difference of the two, right? And of course, in regular linear algebra, this doesn't make sense, but this is about broadcasting, right? So this you will automatically interpret the z as a vector of 3 with 3 entries, each of these entries being identical. This is what NumPy is just doing, and now Gurobi as well. So this is now 3 constraints here, right? That you add with that. And the same for the right-hand side. This is just a single 0, and of course that will be expanded to a vector, a 0 vector with dimension 3. Good. Some more new matrix API, matrix-friendly features in the Gurobi API. So in general, you will just have much fewer surprises when you are working with NumPy and experience with that, and then how shapes and stuff behave in Gurobi. So this just now works pretty well. We have both matrix and element-wise multiplication support, and the mvar objects, you can extract a diagonal from such a matrix variable object. You can convert a list of var objects into an mvar. You can sum along the axis. We have already seen that in the previous examples. You can do element-wise squaring. We have seen that as well. Similarly, linear expressions. So we have all 0 expressions. So you can just say this is we want to have a zeros and just provide the shape, how the matrix should look like, where everything is 0. You can as well sum along the axis. And for the quadratic constraints, this is actually a new class. So now you can all do that as well with quadratic constraints. There's similar features to the linear ones. And then, of course, we need to add also the matrix Q constraint class in order to support the quadratic constraints, which are then the result objects of the add constraint method. Okay, so that's the improvements in the Gurobi matrix-friendly API. And now I'd like to talk a bit about a new thing that we do with Gurobi, or now since November 2022, we have created a few open source GitHub repositories that I'd like to introduce to you now, which deal with certain types of things that are pretty interesting in my view. So the first one is the Gurobi Pandas project here. This enables convenient Gurobi model building patterns with the very famous Pandas package. The second one is pretty exciting, the Gurobi machine learning project that allows users to add a trained machine learning model as constraint to a MIP. These one already exist right now, so you can go to our github.com/Gurobi GitHub page and find these repositories there. So the first one, the Pandas, is currently just in beta stage, but it will be finalized very soon. The machine learning one, that is already in a so to say final state, but of course it will still be improved over time. And then later this year, or maybe at the beginning of next year, we are going to release 2 additional repositories. One is the Gurobi Optimods. So that is a collection of simple to use optimization models for very specific applications. So this is really for people who just don't understand math modeling and just want to get a solution to their problem. And if they are lucky, then exactly their problem is part of that model collection. And then they can just plug in their data and get the solution out without even having to understand what's behind the scenes. And then the other part, that is really for the expert users, the numerical issues assessment tool. So if you have numerical issues with your model, then with that Python package, you will hopefully be able to analyze these models and get kind of the root cause of your numerical issues. So roughly similar to our IIS tool, where you have when you have an infeasible problem, and then you can call the compute IIS function to give you a subset of the model that is still infeasible. This numerical assessment tool tries to give you a subset of your model that still has numerical issues. Okay, you can find these GitHub projects on this webpage that is listed here. All of them are distributed as open source packages under the Apache license 2.0. Good, but I'd like to talk about the two existing ones, which is the first one is Gurobi Pi and Pandas. So you can now create with that package Pandas series and data frames of Gurobi variables, and then you use Pandas operations to combine these variables and data into constraints, and then you can extract the solution data after the optimize call as a Pandas series. And that means all of your data manipulation will stay in Pandas, and there is no need to manually translate between Pandas and Gurobi Pi. So all of the translation layer that is now done with that open source package here that we provide. So here you can see one example, right? So this allowed pairs, that is your input, that is a Pandas data frame, and you plug that into this GPPD. This is the Gurobi Pi Pandas package advars function. Here model, that is the Gurobi Pi model, and then you just specify what is the type of the variables and some names and objective and so forth. And then when you create that, this gives you a Pandas data frame consisting of the same dimensions that you had in this allowed pairs data frame, and the entries of that data frame are the Gurobi Pi variables, right? So this is the output of that. So this data frame obviously had a column project and column team, and then the variables are created regarding these two dimensions. So this package you can find here on that web page, and we have a documentation with read the docs hosted documentation of that. That is very nice. There are complete model building examples using Jupyter Notebooks, and this also contains guidance for writing performant Gurobi Pi Pandas code. So how should you do it to get good performance out of that? So the second package I want to discuss is the Gurobi machine learning package. So what is the goal of this package? So we want to simplify the process of importing a trained machine learning model that was built with one of the popular ML packages and support the process of importing that into an optimization model. Additionally, we want to improve the algorithmic performance to enable the optimization on such models, so that you can hopefully solve your optimization problems that contain such machine learning constraints. And then that makes it easier for optimization models to mix explicit and implicit constraints. So currently, so we are not the first who are working on that or had that idea. So there are other similar packages out there. So these four are just examples. There's the Janos package from Bergman, and they have started in 2019 with that. There's Relu MIP, OptiCL, and then the relatively recent one is the Omelette project at the Imperial College. So here is the list of regression models that currently Gurobi machine learning understands and can automatically translate into mixed integer models. So from scikit-learn, we support a large number of different machine learning regression models. So linear logistic regression, decision trees, neural network with Relu activation function, random forest gradient boosted trees, and simple transformations like scaling, polynomial features of degree 2 and the one-hot encoder, and then pipelines to combine them. So we will see an example of that in a minute. And then from Keras, we support neural networks with dense layers and Relu layers, and then this is either functional, object-oriented, or sequential. And PyTorch, we also support neural networks similar to Keras, so dense layers and Relu layers, But here we only support the sequential models for now. But you are invited to provide additional code to also support more of that stuff. So this is an open source project, so we are happy if people contribute to that to make it more powerful. Okay, so let's look at the scikit-learn example here. How does it look like? So say you have trained a regression model with scikit-learn. So that the output of that, basically your final result, is that regressor that you have. In that case, it is a multi-layer perceptron regressor with hidden layers, or two hidden layers of size 10. And the input dimension would be automatically the dimension here of that X training set vector set, and the output dimension would be the dimension of the Y vectors in the training set. And then the fit function of that pipeline here, this is just scikit-learn, right? So this is the training. So that means afterwards you have a trained neural network. And whatever that means, so often in your applications, this means that you are modeling some real world phenomenon, or you are modeling some behavior of some group of people or whatever. But essentially it is just a mapping from a set X to a value Y. And this is what you learn. This is just a function, right? And now you want to add that function as a constraint to your Gurobi bit model, because you are now trying to optimize the controls that you have over that function that is modeled by that regression, in that case, by the neural network. So how do you do that? So you create a Gurobi model as usual, and then you create your input variables. In that case, you just use the matrix variables of this matrix-friendly Gurobi Pi API. And you create your output variables, and now you add the constraint that should model that neural network here. This is with this add predictor constr function that is part of that Gurobi machine learning package. You provide the model M, you provide the scikit-learn pipeline here that has been trained already, and then the set of input and output functions. And what will it do? It will then internally create all of the auxiliary variables and all of the auxiliary constraints that are needed to model this neural network. So each individual neuron will have this constraint that there is the weight vector multiplied by the input vector, and then this ReLU translation, there you need a new binary variable to model that in order to decide what the output will be, and so forth. And then the second layer, the same, and so forth. So this gives a potentially large number of constraints, and all of that is done automatically for you by that add predictor constraint method. So we have, and now speaking about performance, we have tried a benchmark run to compare 9.5 against 10.0, because with the Gurobi machine learning package, so there's no magic in it. It's just a translation into linear constraints and auxiliary variables. So you can even use it with Gurobi 1.2 probably. But if you use it with 9.5 and compare the performance to that to 10.0, you will see a big difference, because we have added in particular that OBBT function to Gurobi 10.0, which greatly improves the performance on such models that come from these neural networks. So as a test set, we have collected various test sets here and used them to benchmark the performance of the solver. So you see here the list of different individual sets that we tried, and then this is the setup of the experiment. So on relatively old machines here, this is our compute cluster that we always use, with a time limit of 10,000 seconds, and some models have been excluded, and we also excluded those models that cannot be solved by any of the two solvers within the time limit. So, and then you see here the result. So let's try to interpret that graph. So on the x-axis, you have the performance in logarithmic scale of Gurobi version 9.5. And on the y-axis, you have, again, in logarithmic scale, the performance of the Gurobi version 10.0. In that case, only the beta version, because this my colleague Pierre has done these performance benchmarks with the Gurobi 10.0 beta version, but the 10.0 final results will be very similar. So and then in the different colors, you see the different test sets. And obviously, when something is to the lower right of that diagonal, that means Gurobi 9.5 is slower than 10.0. And only those few dots here on the left upper side of the diagonal there, Gurobi 10.0 is actually slower, but you see here a massive number of models on the very right-hand side, where Gurobi 9.5 would hit the time limit of 10,000 seconds, and Gurobi 10 can still solve it. So in particular, that one at the bottom right, so Gurobi 9.5 is hitting the time limit, and Gurobi 10 can solve it. Probably what is that in is it 2 seconds or something? Maybe something like that. Okay, so performance is greatly improved here. The factors give you also the geometric speed up numbers for 9.5 to 10.0. So in this orange test set CCL, it's an 80 times speed up, but of course this speed up is underestimating the true thing because the time limit hits are just counted as 10,000. Okay, here's the page for that Gurobi machine learning package. You can find the package here on that URL, and also there's a read the docs documentation for that so that you understand how to use it. It's open source, as said, with the Apache license 2.0. And with that, I'd like to end just pointing you to additional webinars that we are going to have in the near future.
Thank you, Toby and Michelle. We will now turn to our Q&A portion of the webinar. You can submit a question using the Q&A feature. While we're waiting for those questions to come in, we have a few upcoming webinars to tell you about. Join us for our next Gurobi 10.0 webinar, December 7th and 8th, where Robert Lutza, Senior Developer at Gurobi, will take a deeper dive into the new Gurobi Pi features. In addition, we have 2 webinars coming up in late January and early February, covering Gurobi machine learning and Gurobi Pi Pandas accessors. Lastly, join us in March as we cover the numerical issues assessment tool. Keep an eye on your inbox for an invite coming soon. I believe we have our first question.
Good, thank you, Kathleen. So, David, Robert, any questions that the audience has? Oh, David, I can't hear you, so you may have connection problems.
I see a question here, Toby. So someone asked, the trained neural network models are all MILP type models?
Yes, essentially yes, because otherwise it would be boring, right? So otherwise the neural network doesn't, if the neural network is just a perceptron, so that means it's a linear model, then it is usually not so useful. But yeah, well, if you have like linear regression models or quadratic regression, then this could just be a QP in the end. So it depends on the input. But when we are talking about neural networks, so multi-layer perceptrons, then this will usually get into a MIP. Yes.
Okay, great. Next question. When can we start using version 10 officially without beta version?
So already now. So Gurobi version 10 has been released officially on Monday. Yes, and it was already available last week for those that had an eye on our PyPI page and our download page.
Next question, is there any plan to build something similar to local solver for some common decision problems? For example, faster near optimal solutions for large scale CVRP?
Yeah, so we don't have any plan for providing a specific modeling language for such problems. What we are always looking at is if there is certain structure in a general MILP, for example, that could then add internally algorithms to better solve that and make it faster. So for example, if you have a capacitated vehicle routing problem and model that as a MIP, so then what we could do is to identify the structure and then come along with better algorithms to find good solutions. That's always on our agenda, but not as local solver is doing it with specialized modeling capabilities.
Next question, any reference you may recommend regarding the set covering problem used to better handle products of binary variables?
Oh, reference. So the set covering problem is a very classical one, but I guess the question is not so much about the set covering problem itself, but how the mapping is done. And no, there is no reference, so we are not We didn't write a paper on that, but it's not so super hard. So the point is that you have in these product terms, each product term consists of two variables, right? And what you need to do in order to find a good bilinear representation is that you have, for all of the product terms, you need to find a subset of the variables such that each of the product terms has at least one of the two variables being part of that subset. So the subset needs to cover all of the product terms, right? And that means the problem is relatively simple, right? Each of the product terms gives you one constraint, namely that you need to take at least one of the two variables, and then you just minimize the number of variables that you select.
Okay, next question. Would the open source GitHub repos contain problems like nurse rostering or resource allocation?
Yeah, so this is talking about our Gurobi Optimods repo. That is this repository with individual functions for certain problem classes. And nurse rostering could be one of them. So we are not yet there. So we will start with a relatively small set of functions. And then we will extend it over time. And of course, also the public audience is invited to provide their own functions. So whatever makes sense can be contributed to that repository.
Okay. And there's another one, and I may be mispronouncing this. Are you planning to implement Gaussian process regression for Groovy Pi?
Oh, no, I don't think so. So maybe Robert can step in here and answer that question.
Okay, and then next question. Is there any plan to extend the machine learning package to more complex methods such as graph neural networks?
That is a good question. So I talked to Pierre about that. So strictly speaking, the answer is no. So there is currently no plan to do that, but this is in our list of things that we could do. So yes, we have thought about that, but for now decided that this is for now too complex. So we didn't do it in the initial version, but it could be that we will add it over time. So this depends a little bit on how the feedback is from users like you about our Gurobi machine learning package. If this becomes very popular, then of course our motivation to extend it further will be much larger.
Okay. And we have time for one last question. Do you have any plans to allow custom branching on variables?
No. So we already support the pre-specified branching priorities, where you can just in advance select the priorities for the variables, and then we would always branch on the variable with the largest priority in that list that you provided. But we are not going to support specific branching rules, user-design branching rules through a callback, because that would require us to call the callback function at every single node of the search tree at the time when the branching decision happens. And this is not how Gurobi is designed, because in the parallel framework, that would mean that this function call would need to be done by any of the threads in our contract with the user, which is really important also in particular when we're talking about the Java API and the Python API, is that only thread 0 is allowed to call the callback. And so this just doesn't work in our software design. And for that reason, it would be very hard for us to support that.
Okay, great. And with that, we can go ahead and close the webinar. If we weren't able to answer your question live, we will follow up with you via email. And with that, thank you so much for attending. And we hope that you'll join us for the 10.0 webinar series with webinars in December, January through March of 2023. Thank you so much. Bye-bye.
Goodbye.